Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Mr. Robin Baeyens. Mr. Robin Baeyens has presented to the faculty his PhD thesis on the topic on the climate and chemistry of irradiated exoplanet atmospheres in partial fulfillment of the requirements for the degree of PhD in science, astronomy and astrophysics. He shall now publicly defend his PhD thesis. Mr. Baeyens, you are now invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give you the floor.
Thank you. Spread out. Oké, dankjewel allemaal om te komen. Alles oké? Slide sharing. Ah ja, tuurlijk. Oké. Dankjewel allemaal om te komen. We zijn live op YouTube, dus er kan af en toe al eens een mankementje in zitten, maar we kunnen beginnen. Ik ga de presentatie in het Engels doen, dus ik denk dat ik daarmee met die taal de meeste mensen uit het publiek ga bereiken. Als er iets is, als het niet duidelijk is in het Engels of zoiets en je wilt het opnieuw horen, dan kan ik het achteraf altijd persoonlijk aan u komen uitleggen, dus dat moet je maar vragen. All right, so I will switch to English now, and I will tell you about the topic of my PhD, what I've been working on for the past 4 years, which is, shortly said, simulations of the climate and the chemistry of irradiated exoplanet atmospheres. So, if you look at the night sky, especially on a day like today, for example, you will see, depending on the light pollution in the sky or in the room, you will see stars, and if you look tonight, around early in the night to the south, you might even see this very bright star in the sky. But actually, this is no star. This is a planet. This is Jupiter. And if we zoom in, you can see that it looks like this. If you take a picture with your cell phone through the eyepiece of an amateur telescope, like I did here, and we see the disk of Jupiter, which is quite bright, and around it are 4 little dots, and these are the moons of Jupiter. So Jupiter, of course, is a planet in our own solar system. However, there are other planets in this picture as well. Not planets in our own solar system, which orbit our own sun, but planets around other stars. So if I circle all the planets in this picture, it would look a little bit like this, and I basically put a circle around almost all of the stars that I could see in this picture. And the reason is, on average, about every star has about 1 planet. So this means that planets around other stars, or exoplanets as we call them, are among the most common objects in the universe, actually. Yesterday, I went and checked exoplanet.eu. That's an online archive of all the known exoplanets. And it had there 4,868 registries. So there are already more than 4,000 exoplanets that we know of. All right, so what can we tell about these exoplanets, and what are their characteristics? Well, astronomers like to put things on diagrams, so let's do that. We have here a diagram showing on the horizontal axis the orbital period in days. So this is also proportional to the distance between the planet and the star. And we have on the vertical axis the radius. so the size of the planet, basically. And for reference, I've also put on there the planets of our solar system. So you can see there, the little one is, of course, Mercury, then a little bit bigger, Venus and the Earth, which are about the same size. The next one from the Sun is Mars, which is again a little bit smaller. And then farther out, we have Jupiter, which is the big one. The other planets in the solar system, they are not on this graph because they don't fit, but that's not a problem because now we add the exoplanets. And then it would look like this. So you see that basically almost all of the known exoplanets are at short orbital distances. And the region there, which is around the region where we find the solar system planets, it's quite empty. This is not because there aren't any exoplanets there, but they are just very difficult to detect. And the planets on short orbits are easier to detect. Okay, so you have many different planets of different sizes. But for this presentation, I will focus mostly on the upper left corner right there. And these are the hot gas planets, or also hot Jupiters, as we call them. And these are really gas giants that are very close to their star, so they're highly irradiated. And the reason why I want to focus on these specifically is that they have an atmosphere which is quite expanded and quite hot. So they are actually the easiest to observe and to really look at the atmosphere and to characterize the atmosphere in order to learn something about these planets in particular. And I will explain you how these atmosphere observations work. But first, I will explain you how we can find and characterize these exoplanet atmospheres from the light that we get from them. So each chemical interacts with light in a very unique way. And I show here a couple of examples. On the far left, you see a neon light. So that's basically the glass tube filled with neon gas. And when you put electricity through it, it shines with a very specific bright red color. In the middle, you see fireworks. And you can see, depending on the different chemical element that is added to these fireworks, it will glow with a different color. On the right, you can see the sodium street lanterns, which glow with a very characteristic orange color. And then all the way on the bottom left here, you can see the beautiful aurora borealis, the northern lights, which you can see if you go far north. And these are basically quite close to what we are going to talk about because they are in the atmosphere, of course, and they are caused by ionized nitrogen and oxygen atoms in the atmosphere emitting light at a very characteristic color and thereby wavelength. Why do I say wavelength? Well, because we physicists, we like to correspond color to wavelength, and that is because of the way of the electromagnetic spectrum works. So you can see that here, light has a specific characteristic wavelength, and depending on that wavelength, it has a different energy and a different characteristic. The most energetic light are the gamma rays on the left. And then if we go towards lower energies and larger wavelengths, we enter in the X-ray regime to ultraviolet. Then we have this very narrow rainbow, which is the region where our eyes are sensitive to. So this is the only part of the electromagnetic spectrum that we can see. And then if we go to even longer wavelengths, we have infrared light and radio waves. So when we say that each chemical absorbs and emits light at a characteristic color, we actually can also say it absorbs and emits light at a characteristic wavelength. And this is important because by looking at specific wavelengths and measuring absorption or emission at those wavelengths, we can actually try to trace what chemical is causing this. And we can do this for exoplanets. So especially when the exoplanet is in a certain configuration, like I show here, where the planet passes in front of the observer and the star. And in this configuration, we can really try to characterize the atmosphere by measuring the brightness of the light at a specific frequency. So by measuring the brightness of the light of the star, if the planet passes in front of it, like it's seen here, you can see a small dip in the light curve. Well, we can then take the depth of this dip, or the transit depth, and we can put that on our diagram towards the right. So here we are looking at light with a wavelength of 1.3 micrometers. So this means infrared light, actually. And we put there our transit depth. Now we can try to repeat this exercise, but for a different wavelength. You can look, for example, at a light of 1.5 micron, and then the planet might look a little bit different because there are chemicals that interact with this 1.5 micron wavelength. You see that the transit depth has increased a little bit, and that we have to mark our dot on the right diagram a little bit higher. And then let's finish this little graph. Then we can also look at light at 1.4 micron. And it might be that the atmosphere looks even bigger, that the planet looks even bigger. And we can put the final dot on our diagram. Now, what does this mean? Well, this is an observation of a so-called transmission spectrum. And by now using an exoplanet atmosphere model, we can actually find out the temperature and the chemical that is causing this specific absorption pattern. So we can add our model to the data, and if they correspond well, like here, which is by design, of course, we have found a water absorption band. So here, in this way, we can actually say, for example, there is water in this kind of atmosphere. All right, so a little recap of what exoplanet atmosphere observations have found already. Here you can see the different chemicals that have detections for exoplanet atmospheres. They're not all very well detected, but some are more hints because the data is very noisy and it's very difficult to do these measurements. But an often detected molecule is water, like I already mentioned. And I have to say, this is water in the gas phase, so not liquid water like we think of water here on Earth, but it's gaseous, of course, because these planets are way too hot for liquid water. And other different chemicals that we can find are Na, which is sodium from our street lanterns, also potassium, and then we also have found indications of titanium oxide, vanadium oxide, HCN is hydrogen cyanide, CH4 methane, and CO and CO2 carbon monoxide and dioxide. So this is all very interesting, but we can also look at the physical structure of the atmosphere, not only the chemical elements that are present there, but also what is the physical state of the atmosphere. For example, from your physics course, you may remember that if you have a hot gas, it expands, and if you have a cool gas, it contracts. So the size of the atmosphere, the thickness of the layers tells us something about the temperature of that atmosphere. It also tells us something about the weight of the atmosphere, because a heavy atmosphere will be more compressed, of course. And then we can make, for example, a distinction between a light atmosphere composed mostly of hydrogen and helium, like we expect in the gas giants, or a heavy atmosphere, like here on Earth, which is composed of nitrogen and oxygen. And then another aspect that we often encounter in exoplanet atmosphere models are clouds. These can sometimes block the signal and then mute the absorption bands that we can detect from these atmospheres. So this is also a very important aspect, and we have to understand how these clouds work. And finally, we can try to derive from these measurements the ratios of chemical elements. For example, the carbon to oxygen ratio, or the amount of heavy elements with respect to light elements. Now, why is this so important that we do all these exercises about planets to understand planets that we actually will never reach because they are way too far away? Why are we concerned with all this? Well, for me, there are basically three different reasons, or three different categories of reasons, maybe. And the first one is to be able to say something about extraterrestrial life and habitability of other planets. So, of course, a very important question that I think most of us have once thought about is, are we alone here on Earth? Or is there also life out in outer space? And by studying these atmospheres, we can actually try to look for Earth analogs. We can try to analyze the climate, the temperature, the clouds, and see if these are suitable for the development of life. And we can try to find biomarkers or biosignature gases. These are gases in the atmosphere that may reveal the presence of life on such a planet. A well-known example is the oxygen in our atmosphere. The reason why our atmosphere is full of oxygen is because we have plant life and cyanobacteria and algae that do photosynthesis and produce the oxygen in our atmosphere. So this is an example of measurements that we could do to infer life on different planets. The second reason is to be able to say something about the formation history of planets. Because, as I mentioned, these ratios that we can find, the heavy element to light element ratio or the carbon to oxygen ratio, these actually correspond to the position where the planet was formed in the protoplanetary disk, far away or close to the star. And thus, it tells us something about the formation process of these planets. It is quite important to know whether the formation of planetary systems is the same everywhere or whether different scenarios are possible. And by researching this aspect, we can also tell something about our own solar system. How was it formed? And is our own solar system in some way special, or is it very common? And then finally, maybe more difficult to grasp, but we can also reach some knowledge for our own Earth. Because our own Earth also has an atmosphere, of course, and we can do atmospheric studies with it, but we can't do experiments with it. Even though with climate change, it sometimes looks like we are experimenting with the atmosphere to see what would happen. But in principle, we cannot do it, and we can use exoplanet atmospheres as a sort of cosmic laboratory in that case. So we can look at the different states or different outcomes of atmospheres on planets to see how these systems behave under different conditions. And this will be able to tell us something about our own Earth atmosphere and about how unique or not unique it may be. Okay, so I hope to have convinced you now that what I've been doing for 4 years is somehow important. And there is a problem. Of course, there is always a problem in science, and there is a problem with modeling exoplanet atmospheres, because often this data that we get from them, it is fitted with one-dimensional models. So very simple models that approximate the whole area of the planet, so the whole atmosphere, as a simple one-dimensional atmosphere with maybe only one temperature, with a fixed chemical composition, irrespective of where you are located on the planet. And this is probably not the case, because exoplanets are, and especially irradiated exoplanets, are intrinsically three-dimensional objects. As you can see from this artist's impression, you have a very strong irradiation on one side of the planet, and you have a cooling on the other side of the planet to outer space. So this can basically induce a very big temperature difference, and this will change the spectral signature that we see from both sides of the planet. This situation is also permanent, because it can be assumed that these planets are tidally locked or synchronously rotating. This means that one part of the planet is always turned towards the star permanently. So if you put this otherwise, the orbital period, so the time it takes for the planet to go around its star, is equal to its rotation period, the time it takes for the planet to turn around its own axis. So if you stand on this planet and you look towards the star, you can do a whole year, a whole orbit around the star, and you will always keep looking at the same star. So you have a permanent day side and a permanent night side. You can imagine that this gives a huge contrast between the day side and the night side in the physical and also the chemical state of the atmosphere. However, maybe it's not the case actually, because you also have very strong wind systems on these planets. The most important aspect, or one of the most common aspects to think of, is that there is a very fast wind jet, a jet stream, that goes around the planet in the eastward direction along the equator. And this somehow redistributes again this energy, and it might erase the differences between the day side and the night side in terms of temperature or chemical composition. So what I wanted to answer with my thesis, basically, are these three questions. First, what chemical diversity can we expect in irradiated exoplanet atmospheres? Second, these three-dimensional effects, can they somehow be observed? And third, what are the biggest uncertainties in exoplanet models? Because often, of course, models have uncertainties and models are never perfect, so it's good to know where we need to improve. All right, and how did we go about researching all these different aspects? Well, actually, I tried to be a bit like Frank de Bozer and make a weather model, or actually I should say a climate model, because it really concerns the whole global planet. And then it looks a little bit like this. So here you can see the simulation or one of these climate models. And you can see on the left, the day side, temperature is hotter there. On the right and slightly towards the back is the night side, where it is colder. And you can see a very dynamic wind system. So you can see in this simulation different waves that are traveling through the atmosphere. And with a little bit of imagination, you can also see this very fast equatorial jet that goes around the planet in the eastward direction. All right, so we can use these kind of climate simulations to estimate whether the atmosphere will be homogenized or not, and how much mixing is going on in the atmospheres. And this is very useful to answer our questions, of course. First, we applied this kind of model to two different exoplanets. Here on the left, we have HD 209458b, which I call HD 20 from now on. And on the right, we have WASP 43b. They are quite similar in some ways, but they're also quite different in some other ways. And that's what makes them interesting to compare them. The similarities is that they are both well-characterized transiting hot Jupiters, and especially the temperature, as you can see there, is around 1400, 1500 Kelvin, so very close to each other. Both planets are very well studied with observations, so we have some data to find out whether we are correct with the models or not, or close with the models or not. There are also some differences between the two planets, and these differences are mainly here, where HD20 has a mass that is lower than that of Jupiter, but a radius that is higher than that of Jupiter. So it's actually quite fluffy, so to say, and the gravity is rather low, and it's not very dense. Whereas WASP 43b is the opposite. He has a mass that is almost twice the mass of Jupiter, and a radius that is a little bit smaller than that of Jupiter. So this one is very dense. The rotation period is also different. The first one has a rotation period of 3.5 days, and the other one has a rotation period of only 20 hours. So this is a really fast rotator, and this induces, of course, dynamics in the atmosphere. The comparison between the two, having a similar temperature but other characteristics that are not similar, makes them an excellent test case for dynamic climate studies. And I will show you the results of those studies here. First, we have a look at a temperature map of HD20, and you can read this map a little bit like you would just read a normal world map. So you have the latitude and the longitude, and the map is centered on the substellar point turned towards the star. So the day side goes from -90 to +90, and the night side are on the edges of the plot here. What you can see here is that there's a temperature difference, but it is not particularly huge. So there is some circulation and heat redistribution. And you can also see this very fast wind jet again. If you look towards the equator, there you can see that it crosses at 0 latitude, and it's a very fast wind going in the eastward direction, like I mentioned earlier. Now, if we have a look at the different simulation, WASP-43b, we can see that it is similar in some ways, but we can also see some differences. The temperature contrast is bigger, so the day side is hotter, the night sides are colder, and we can see that the fast equatorial jet is somehow disrupted. So it appears that due to the climate dynamics in this model, there is something else going on, and that leads to a different type of climate or a different climate regime. Now, we looked into this and we found that WASP-43b has a fast rotation, and that induces a wind jet that goes very deep into the planet, whereas the wind jet on HD20 remains quite shallow into the more observable layers of the atmosphere. This deep wind jet in WASP-43b induces some dynamical feedback, which feeds momentum from the deep atmosphere, which is a huge reservoir of momentum, towards the upper atmosphere. And this reduces the heat redistribution and disrupts the equatorial jet stream a little bit. Okay, why is this now important? Well, actually, this is a particularly interesting result because up to now, in climate modeling, it was assumed that the observable atmosphere and the deep layers were disconnected from each other. And now we show that actually they in some cases, and mostly the cases of fast rotators, they are connected with each other, and we cannot neglect the deep atmosphere. Usually, this was sometimes done because if they are disconnected and you are only interested in the upper part of the atmosphere where the observations come from, it's not so important to have the temperature state of the deep atmosphere right, of course. So, to summarize, the gravity and the rotation rate here add some climate diversity. And we later also verified this with a grid of climate models that went beyond these 2 exoplanets, but really for a whole range of different temperatures, gravities, and also different stellar types. And we found indeed that for these very dense and fast rotating planets, this always seems to be the case. We thus find an important physical coupling between the upper and the lower atmosphere that could be important. All right, so now we continue to the next part, and that has more to do with the chemistry. And to do that, I will introduce you to the 3 distinct chemical regimes in an exoplanet atmosphere. So here I show them some different molecules, some of the most common molecules again in a plot, where on the horizontal axis you see the molar fraction, or basically the concentration of this molecule in log coordinates. So this means on the far left means the concentration is really low, on the far right means the concentration is high, and the vertical axis is just the altitude in the atmosphere. You can see that the atmosphere consists mainly of hydrogen and helium, as expected with gas giants, because these are just the most abundant elements in the universe. And then we also have quite a lot of CO and H2O in this planet. But I also show methane and ammonia, because this here you can see some interesting behavior. There are 2 lines plotted for each species. The dashed line corresponds to chemical equilibrium, and this means if the times are long enough, or if each molecule has a long enough time to react with other molecules, then eventually it will reach a stable state, and this is what we call the equilibrium. However, the solid line that I plot here is a more realistic estimate of what is the chemical composition, where we also introduce other effects that can affect the mixture, like mixing and photochemistry. So you can see in the deep atmosphere that chemical equilibrium seems to be valid. This is also as expected, because you have a high pressure and a high temperature, and each chemical species has a lot of collisions with other species, and then can react to its stable state. However, if you then go up into the atmosphere, the pressure and the temperature both drop, and at some point, the dynamics of the atmosphere will take over. So there you enter in a regime where you have mixing. Here, for example, if you look at methane, you see that the methane abundance remains in this layer almost constant. And that is because you have constant mixing from the layers above and below that are actually mixing the methane throughout the atmosphere before it has a chance to react to different species. All right, and why doesn't the composition of methane here remain totally stable? Well, if you go to the upper atmosphere, the uppermost layers, then you have photochemistry. And photochemistry is basically the interaction of UV light. It can also be other light, but UV is more energetic, so usually UV, that hits one of the molecules and it can dissociate in different species. You can see from this graph that methane and also ammonia, NH3, are both very susceptible to this kind of dissociation, and they will be quite easily destroyed in the upper atmosphere. However, this frees up some carbon and nitrogen atoms, and these can then form again together to make, for example, hydrogen cyanide, which is then rather abundant in the upper atmospheres. All right, so if you listened very carefully, maybe you have thought, okay, but this is again a one-dimensional view, and didn't you just say that exoplanet atmospheres are intrinsically three-dimensional? Well, that's of course true. So we have this kind of situation on different locations of the planet. Here I plot a similar type of diagram for different locations on the planet, which I try to illustrate here with these little X's across the equator. And you can imagine for each of these locations, I plot again a dashed line and a solid line. Especially for methane, it is very clear that depending on the location where we are at the planet, the methane content will be different in the atmosphere. This makes sense because methane is quite temperature sensitive, and the day side will be warmer than the night side, so there you will have less methane than on the night side. However, this is a case where I didn't incorporate horizontal wind or advection in the horizontal direction. So what happens if we do that? Well, if we introduce one of these very fast wind jets, then we can see that the picture changes like this. So we have the jet stream that homogenizes the whole composition. We are in the upper layers of the atmosphere, so the chemical elements don't have enough time to react to different things, and our whole composition is actually mixed together and homogenized. So we see that all of these lines now fall at the same location in our diagram. And that location will be more close to the day side composition than the night side composition. All right, so how does that now introduce chemical diversity, or is this now, how is this extrapolated to different types of planets? Because now I just show only one planet of around 1400 Kelvin, but we also did this modeling exercise for a whole grid of planets, and I show a small subset of that here. So you can see here many different plots, so please don't be overwhelmed. I will just guide you through it. And it's all of these different figures next to each other that I just showed you. On the top row, we have the colder planets. We start at 600 Kelvin, and if we go row by row, we end up at 2200 Kelvin even. So really quite hot planets. And we also show in the different columns planets around different stellar types. Now, this is a messy plot, but I just want to highlight one particular thing in this plot that is quite interesting. And that is that there seems to be a dichotomy between the cool planets on the one hand and the hot planets on the other hand. So the cool planets, they tend to be chemically homogeneous. We always have for each different color, which is a different elemental chemical species, we have that these lines all fall on the same plot or on top of each other. And for the hot planets, we have these lines falling in different positions in the diagram. So there we have, depending on the location, a different chemical composition. So potentially large day-night differences in the chemistry. All right, so to summarize this, we have the dynamical mixing, the horizontal wind here, creating a dichotomy between the cool and the hot exoplanets. We took into account the vertical mixing and the horizontal mixing, which we derived from our earlier climate simulations. So it should be more or less self-consistent. And it appears that it will be important to take into account the three-dimensional structure of hot exoplanet atmospheres, mostly hot exoplanet atmospheres, because there we saw that the horizontal mixing there we saw that horizontal mixing was not efficient enough to remove all the chemical horizontal gradients. In the cool planets, we might get away with using a one-dimensional chemical model, for example, but only if the temperature is right. Because what we also saw is when we synthesized a lot of model transmission spectra, that the signature in the transmission spectrum is basically driven by the temperature and less so by the chemical composition. So the takeaway message here is that you will have to have the chemistry right, the temperature right, and then the chemistry will follow. And in the case of a cool planet, you can get away with using a one-dimensional chemical model. There is also one additional thing that I would highlight here, and that is connected to the vertical mixing, which can actually make a connection between the deep interior of the planet and the upper atmosphere where our observations are coming from. And in comparing the results of our chemical models and our transmission spectra with earlier work of other research groups, we found that this is an important connection because we found some differences there, and we derived that these differences were due to a different deep state of the atmosphere, where the deeper layers of the atmosphere, they can have a different temperature, and as they have a different temperature, also a different chemical composition. And if the vertical mixing is then deep enough, this chemical composition is carried throughout the atmosphere to the observable layers. So here we again find this connection between upper and lower atmosphere, but now for the chemistry. This is actually a problem because it is quite difficult to know what the temperature of the deep atmosphere should be, because there are many different physical processes that can affect this temperature, and we do not know very well from our climate models. We cannot really derive self-consistently what the temperature should be yet. So this is a good line for future research. An additional problem here is that the vertical mixing efficiency is also not so really well constrained. And actually, it can vary by orders of magnitude, maybe even be different on the day side of the planet and the night side of the planet. So this is also a good line for future research. Then we still haven't talked about the last chemical regime in our planet, and that is the photochemistry. And here we can actually be quite short with a poignant conclusion, namely that photochemistry seems to be negligible when we try to synthesize transmission spectra from our models. And I can show that here with these two different transmission spectra. On the gray, we have the situation without photochemistry, and in green, we have the situation with photochemistry, which are plotted on top of each other. And you can see that there seems to be almost no difference. There are a few little differences, which I annotated. For example, in the top plot, you can see that there is a little peak of hydrogen cyanide when you include photochemistry, but it's not such a big peak, and it will be difficult to observe. And in the bottom plot, you can see that there's some reduction in the absorption bands of methane, but also the reduction is very small. So it will be very difficult to observe these kinds of effects. Does that mean that the chemistry is not affected by photochemistry at all? No, not really, because actually in the upper atmosphere, it is quite important. We find that our upper atmosphere in our models is strongly affected by photochemical dissociation. And we even found products of photochemistry on the night side of our planets, which is, and they arrive there actually by being transported by a horizontal wind towards the night side, from the day side towards the night side. However, on the spectrum, it has negligible impact just because we are not sensitive to these upper layers, but we are more sensitive to the middle part of the atmosphere, where photochemistry is not so important. However, if we use different observing techniques, for example, then we could try to observing techniques that are maybe better in the higher parts of the atmosphere, then we could really try to research the effect of photochemistry there. All right, so now if you've all listened very well, we can all together answer these questions that I've posed in the beginning of the talk. So what chemical diversity can we expect in irradiated exoplanets? Well, besides the equilibrium temperature, which of course has a huge impact on the chemistry and the climate, we also find a strong diversity within planets of the same equilibrium temperature. The rotation rate and the gravity can give rise to different climate types, such as like we have seen between WASP-43b and HD20. And they can also give rise to transitions in the chemistry, in some cases, between CO and methane. There are still a lot of parameters left unexplored. For example, changing the elemental composition that we begin with, or changing the intrinsic temperature, the UV irradiance. But many of these different parameters, we aim to do a follow-up study, especially for the intrinsic temperature here, in order to find out how they will further change and introduce chemical diversity in exoplanets. If we want to answer the question whether 3D effects can be observed, then I would say yes, not with future instruments, or it will be difficult with, not with current instruments, or it will be difficult with current instruments, but with future instruments like the James Webb Space Telescope, it should be possible. Because the differences introduced in a transmission spectrum should be big enough to detect with the James Webb Space Telescope. Of course, we will need to be able. We will need to wait until it has launched and see what sensitivity it actually reached. But in principle, it should be possible. And like I already mentioned, the cool planets, they tend to be chemically homogeneous. So there you can do with a 1D model. In the hot planets, a 3D model would be better. And then finally, what are the biggest uncertainties in exoplanet models? I think you might already have a clue about that. That is, of course, the deep atmosphere. We found in different parts of our work and in different parts of the thesis, we found a dynamical feedback, but also a chemical feedback between the observable layers and the deeper layers of the atmosphere. So this is definitely an important line of future research to go to. And then finally, I want to end with a slide that I put in my first outreach presentation as a PhD student, which I gave at the Public Observatory of Baeyens. And that is about the James Webb Space Telescope. And I've updated this slide ever since. So you see that the launch date of the James Webb Space Telescope has been postponed a few times, but I'm fairly sure now, 18th December, it will be the day we will watch the live stream together, Yannis, and then it will launch, and this can potentially revolutionize exoplanet science. Because the James Webb Space Telescope, it will have unprecedented sensitivity, especially in the infrared, where we are detecting all these molecular transitions. As I said, it should be sensitive to these three-dimensional effects, and we will hopefully be able to constrain better the physical and chemical processes in exoplanet atmospheres. We will also hopefully be able to go slowly towards cooler exoplanet atmospheres and maybe even rocky planets to work ourselves towards Earth-like planets in the end. And then a little bit further into the future, we have also the Ariel space mission, which is the first mission that's going to be dedicated to exoplanet atmosphere studies. It will do a statistical study of about 1,000 planets and thereby assess the chemical diversity that we can see in all these different interesting objects. So there is definitely a lot to come in the future with new instrumentation and exciting times for exoplanet science. And I hope with my thesis that I have been able to contribute a little bit to that future. Thank you very much for listening.
Thank you very much, Mr. Baeyens. First of all, I'd like to introduce the members of the examination committee. Microphone, is this working? Yes. So we have the supervisor, Professor Leen Dessin, from the Department of Astronomy and Astrophysics at KU Leuven, the co-promoter, co-supervisor, Ludmila Caron, from the Max Planck Institute for Astronomy. We have then, three members from KU Leuven, Professor Jun Sundquist, Professor Connie Arts, who could not join today, but she was present for the preliminary defense, so she had ample time to ask questions. Professor Minto Nguyen, who is not here but should be present online. And then two external members, Dr. Antonio Garcia Munoz from CEA Saclay in France, and Dr. Paul Brandon Rimmer from the University of Cambridge, who is also excused. He could not attend today, but he also attended the preliminary defense. And I am the chair of the examination committee, Jérôme Laurent. So I will start with the external member, Dr. Garcia Munoz.
Hello, yeah, can you hear me?
There you are. Yes, we can hear you.
Okay, so since we had ample time before to ask questions, I'm going to be quick this time. There's one question about targets. You have mentioned WASP-43b and HD 29459b, and I was just wondering if there are any other targets that are going to be observed by JWST that will be particularly interesting to test your ideas.
All right. Yeah, I think if I talk like this, I talk to you. Yeah, okay. It's a little bit strange setup. Okay. Yes, there will be many different targets observed with James Webb. Some part of the proposals that have already been guaranteed, and some part of the new ones. I don't have a good list in my head about these targets, but I think very important is also just the reobservation of many of these planets that we currently know and that I already talked about as well. So, for example, WASP-43b, it will have a phase curve observation, which will be a very, well, a better way to really constrain the temperature structure of the planet, and for the first time also see the heat redistribution in this planet very well. So there are probably also many other interesting planets, but I don't know them by heart. I would say that, yeah, with James Webb will be so much of an improvement over the Hubble and some Spitzer measurements that we already have, that any different hot Jupiter could be an interesting candidate, depending on which science case we are interested in.
Okay, and then I have a couple of other questions, more general, less technical. One is, what is the main takeaway, or well, what is, in your opinion, the main finding of your thesis? And if you can tell us something that you were looking for in the thesis and in the end didn't work out, just to have a perspective.
Yes, all right. In the end, we set out to, or in the beginning, I think we set out to observe or to model clouds in the atmosphere first.
Mm-hmm.
But then, before we could do that, we actually found out that there are many different basic aspects of exoplanet climate and chemistry that are not very well understood. So we have these hugely complicated models. There are 3D models. There are a lot of physics in them, and they are quite difficult to understand. So we wanted to try first to test these models for a very big parameter range to see what would happen, what would be the diversity in exoplanets that we could observe, rather than maybe focus on a few different exoplanet test cases that maybe happened previously. So the main idea, I think, in the thesis is to gain a little bit of a feeling or to gain an intuition on what processes, chemical and physical, will be important or will be at play in exoplanet atmospheres, and in what region of the parameter space, for example, temperature, gravity, rotation rate, etc. So in order to basically gain an intuition of what we could expect there, including all the three-dimensional effects and difficulties that come with that.
Okay, what? Well, last question. Like, you are starting now, probably a career as a senior researcher, and where do you see yourself in 5 or 10 years, and how do you see the field?
That I think that is the most difficult question of
Yes.
all of them. So I can already answer it for the first 1 year. So
Okay.
I will do a postdoc of 1 year here at KU Leuven, still continuing the research because there are many questions unsolved. So, for example, we want to try to repeat a number of observations with, for example, a different intrinsic temperature, which changes the deep atmospheric layers, to see whether that can, what would the effect basically be. And we will also, we have now in the group also an updated version of the model, of the GCM model that I used in the thesis here, which includes realistic coupling between radiative transfer and dynamics, whereas I used a more parameterized version. And I think we still have many ways to go with that kind of model. So that will be the near future, and then in the further future, I don't know yet. So
okay, it's fair enough. Not to say it's a difficult question. It's
yeah, we will have to find out.
Okay, so that's everything from my side. Best of lucks and best wishes for the future. Yeah.
Thank you very much.
Thank you. I now turn to Professor Sundqvist.
Oh, yes. Yeah. Hi, Robin. I can stand up, I guess.
If you stand near the stand, then you will be in the view of the camera.
So I should not do that.
There.
My gown
Exactly.
is so long. Yes. Okay. Thanks very much, Robin, for a very nice presentation today as well. And these
these estimates of one planet per star on average. First, it's on average, so that means that there are many stars, for example, in the Kepler sample, where there are no planets found, but there are also several systems where there are multiple planets found. Secondly, they have huge error bars, these statistical measurements. So it will depend a little bit how future missions will find new and new exoplanets. And I don't know if this result will hold up, but I can imagine that it will it might not be one per star, but in principle, just by the sheer amount of planets found in the Kepler sample, we know that there are many in principle. So I think it may not be exactly one per star, but it seems realistic.
It's a good order of magnitude estimate,
yeah,
you would say.
Indeed.
Okay, so what about your distribution then? Because in your diagram also you show them that's of course a clear bias, that it's easiest. Do you think that will that distribution also hold? Are there a lot of planets? Are there preferentially at low orbits or at short orbits? Or if, well, in the far future, do you think that they will be evenly spread out, or what do you think there?
Well, I think this distribution will, of course, as you said, it's a clear detection bias. So we will have many different planets at larger orbits as well. It might be that, I don't know, well, I wouldn't be able to say whether they are evenly distributed among orbital distances, or whether there might be clumps of different, of higher frequency at a specific orbital period. I think it could be the case that short orbital distances are maybe not favored, but are maybe a little bit more frequent, because we have tidal interactions in planetary systems, and we have also migration, so planets can migrate. We know that from the existence of hot Jupiters, they are formed probably further out, and then they migrate inwards, and at some point this migration stops, and then they end up on a short orbit. So it could be that by this kind of effects, you can have sort of different clumps where some planets are more favored. But just, I think that depends strongly on the theory of planet formation. And I don't know if that is well known as of yet.
Okay, thanks a lot. So let's go to discussing then a little bit more your models. So one thing I was wondering, you mentioned it at the end, was this uncertainty of the deeper layers and the deep circulation models. And you mentioned that, okay, but we can try to model it all the way from the interior. Wouldn't it also be a possibility that you just invoke it as a lower boundary condition in your type of modeling, like a turbulent lower boundary? Is that something that you have attempted, or somebody else, or do you know? What do you think would change if you did that kind of modification to your models?
To my models specifically, I think it will be difficult to do it like that, because the resolution of these kind of models is the resolution is low, so the distances of the grid cells are big. And I think to model it in a good way, probably you will have to have, at some point when you reach from the radiative envelope, a convection layer at some point. You will need to have that kind of feedback of the convection as it pushes towards the radiative envelope, and maybe it can cause gravity waves like that, for example. I think it's important to include that. I don't know whether it will be a very strong effect, but if we were to research, or whether we want to, find that out, then we should include it, of course. And that will be very difficult in these types of models. So maybe I was actually more thinking along a line of having a higher resolution model, maybe with a kind of 3D box that simulates only just a small part of the exoplanet atmosphere rather than the whole, and then start to scale up from there to see whether this small box already gives you something to work with, whether there is some behavior that can be translated to the bigger scales.
Okay. Yeah. Thanks. And then another thing that you mentioned just at the end, that was clouds. How could you treat? Because you also said that that might be observable. Can you explain what you meant there? If you have significant clouds in the atmospheres, and also, can you give us some sort of hint? How would you go about to include that then in the modeling technique and in the comparison to the observed transmission spectra?
Yeah. All right. So how the clouds can be observed, that is basically by cutting off the transmission signature at some point. So if I were to observe a cloud-free atmosphere, for example, I could see a very big transmission absorption band of water again, for example. But it could be if there's a cloud layer at some point, you only see the top part of that water absorption band, and then just a gray continuum. There are also clouds that have some sort of spectral information, and especially if you go towards the wavelengths that are even further to the mid-infrared, then you could maybe see some spectral information of the cloud itself. So this is also why James Webb will be quite important, because we will have the wavelength range there. So we can distinguish between, for example, different types of clouds. And if we were to include clouds in our atmospheric models, there are a number of different ways to do that. You can, for example, sometimes it's called to paint on the clouds. So they are not included in the model itself, but they are just as a sort of equilibrium cloud in post-processing. So that is one way to do it. Probably not the most realistic way, because they have strong radiative feedback via greenhouse effect and reflection effects, for example. So you could also introduce cloud particles in the GCM itself and have it radiatively have a radiative feedback between the cloud particles and the atmosphere. And then the model becomes much more complex, much more heavy to calculate as well, so much more computationally intensive. But that is a way that you could do it. Then
that would be something like aerosols, or
aerosols, like tracer particles, and then there are different ways to do it. Also, to also incorporate a cloud formation, then, because the formation of clouds in hot Jupiters is not so easy, because here on Earth the clouds are formed when species just condensate on grains that are already there, for example, ash or dust in the atmosphere as aerosols. But on hot Jupiters, you will have to have a nucleating species that will condensate first, because there is no surface and the temperatures are really high. So we'll have, for example, a cluster that will form first, and then something could condensate on there. But to include all this microphysics, that would become very difficult in the model. So often you can also often it is also just assumed that clouds form after, for example, a temperature threshold has crossed or something like that. That would be a little bit more parameterized, but a little bit cheaper, computationally cheaper way to include it.
Okay. Yeah. Thanks. That was basically it from me. I will actually, I guess I can finalize then with the question also, in the spirit of the first that I also ask a little bit more of a public. So you've been analyzing these hot Jupiters in quite some detail, right? And we saw from your diagram, and we discussed the diagram, that there are a lot of them. They're easy to detect, so that makes sense. So, but you also mentioned that one of the big goals, of course, is to see, could there be life outside our own sun, so, outside our own Earth? So yeah, simple question. Do you think, could there be life on hot Jupiters?
Yes, I don't think so, actually. We know that life can arise in many different states. For example, here on Earth, you can have even in high pH, very acidic environments or very high temperature environments. But I think on hot Jupiters it will probably be very difficult because as I have talked to people who are studying prebiotic life, usually a medium, a liquid medium, for example, water, is not necessary, but highly inducive for the formation of life as we know it. Also, just a surface could help a lot, and just the temperatures should also probably be lower than those of hot Jupiters. So that is to say, for life as we know it, probably you would need rockier planets with colder temperatures. For life as we don't know it, who will answer that question?
They may also not be so sensitive then to a permanent night, as life here would be, perhaps. Okay, thank you very much, Robin, and yeah, congratulations. A very nice piece of work.
Thank you.
Thank you. I now turn to the two supervisors. Do you want to ask questions?
Okay, you said at the very beginning that one of the things that you can... Oh, okay, sorry. So one of the things that you can, in principle, figure out is the formation history, and with elemental abundances in the atmosphere. Can you say a little bit more about this and how your chemistry also may be important to understand this? Or what do you mean with formation history and abundances, and how is this connected?
Yeah. So one of the diagnostics that I mentioned that could teach us something about the formation history is, for example, the carbon to oxygen ratio. You have in the protoplanetary disk, so the big disk that forms around the young star, there is a chemical gradient in that disk, just because the temperatures change, or the temperature changes if you go outward. And at some point, you will have a temperature that is low enough for a specific species to condensate. For example, water can condensate from the gas phase towards the solid phase, and then we call this the snow line. And then this water will remove oxygen from the gas mixture. You can also have, for example, carbon monoxide. If this condensates, it will remove the same amount of carbon and the same amount of oxygen. So by having a look at what is the carbon to oxygen ratio, we can actually try to find out where in between these different snow lines, where these different molecules condensate, where it was formed. Just because these gas planets are assumed to accrete the gas from around it, and it will then, well, accrete gas with a different elemental composition. That can also change the atmospheric chemistry, because if you accrete gas, which is, for example, highly carbon rich, you will also encounter more carbon rich molecules in the atmosphere. So more methane rather than CO, for example, and also maybe more complex carbon molecules.
Thank you very much. And my second question is also related to the low boundary, or maybe a different part of the phase space. So you went with the temperatures quite high, up to 2000 Kelvin. And at this stage, is actually hydrogen dissociates into ions. So what other physical effects might be important there? For example, magnetic fields. How do you think you can couple? Is this important in your research? And if it is, how would you tackle this in the future?
Can you repeat for planets higher than 2000 Kelvin?
But temperatures higher than 2000 Kelvin. Yeah. The hydrogen associates into ions, and then if you have magnetic fields, will this affect your climates and your chemistry? And if yes, how do you tackle this? How do you want to tackle this in the future? Yeah.
So yes, it will have an effect, especially the ions. They will have a strong opacity. For example, also in the, not only in the infrared, but also in the visible light. And because of this strong opacity, they can actually create inversion layers higher up in the atmosphere, and that will change the vertical temperature structure quite significantly. But this is with the new model that we have now, which takes into account radiative feedback. It's quite easily, so to say, included by just including these opacities of all the different species and ions that are needed. It might not be totally clear which ions are needed, but we have some ideas. And then magnetic fields, well, they can have a whole range of complications. For example, you can have the magnetic fields in the deep interior again, where they couple to the gas and they can create heating. So this is one of the ways that I mentioned, that you could heat the interior atmosphere, which will probably have a feedback on everything, on the climate type and also on the chemistry, if the vertical mixing is strong enough. But there can also be other effects of magnetic fields. I think there has been some study done about this, where they included, where they used an MHD model, magnetohydrodynamics, and where they found that there was a coupling so that the hotspot shift is not towards the east, but towards the west of the planet. So this is also a different type of climate. And as you know, there are some planets that do show westward hotspot shift. So this is one way to tackle that problem. But I think in general, the information that we have about exoplanet magnetic fields is still very limited. So I think there, hopefully from observations, we would be able to derive some more constraints on that.
Okay. Thank you. That's on me.
I'll give the floor to the supervisor.
Robin, normally I don't ask questions as a supervisor, but sometimes there are exceptions. Yeah.
Okay.
So maybe first for the people here, you have been discussing the radius of planets, the radius of gaseous planets, but can you explain to the audience how you define a radius for a gaseous planet?
Okay. So usually the radius for rocky planets first is very easily set just by looking at the difference between the temperature, between the interior, the center of the planet and the surface. For gaseous planets, it's actually not so easily set, and it will depend a little bit on the approximation or on the assumptions that you make there. Usually for these types of diagrams that I showed here, it is just the radius in white light, so that you measure here in the transit, in the transit depth in white light. But as you have seen, depending on the wavelength range, this can change. So actually, it depends until where the radiation penetrates, where you can set your radius, and then on top of that, you can start speaking of your atmosphere. Another way to do it, which is my preferred way, is to just pick one reference pressure and say at 1 bar I define my radius, and then you can start talking about an atmosphere from further out.
Okay, thanks. And then another question that potentially could confuse you. But if you have a tidally locked planet, how do you then define east? You know, I'm always confused. I always like to lose my way. Also, when I came here today, I crossed Leuven 3 times. And for people who are not astronomers, you normally have north, east, southwest. But when we have images of the sky, just to confuse me, we just do it the other way around. So images in our publications, they have north, east, southwest. So just to let us confuse. Now back to you.
Yeah.
How do you define it?
So how we define it here, and I think that's usually how it is done, is define east as prograde. So we look at the rotation of the planet itself. It has one rotation axis and it will rotate like that. So Along the rotation is the eastward direction. Against the rotation is what we call the westward direction. And then we have north and south.
Thank you. And then a more technical question. So you have been showing how methane is extremely sensitive to the temperature. So what do you then recommend when we will be using James Webb space data and we are aiming for instance, a detection of methane? How should we understand these detections given the fact that you have shown that depending on the location of your planet, you might have such a different methane abundance structure? So what is then the way forward?
Yes, so there are many processes that can also change the methane composition. So I think by doing these kind of modeling exercises, I think this is a way to basically equip ourselves with a set of assumptions that may or may not be valid. For example, if it is a cold planet, as I said, the chemistry will be or can be assumed to be homogeneous, in our models at least, if they are correct. Let's hope so, but we think so. And well, because they are homogeneous, you will not be able to see any differences there, depending on the location of the planet. For hotter planets, it will be, of course, more difficult. Then we can also try to constrain, for example, we can well, look at the geometry of the problem. In a transmission spectrum, you only see the ring around, or the two terminators, right? So we can focus our attention on that region of space and see if we then expect a difference between those two. And if we have very good observations, it could also be, especially for hot or ultra hot Jupiters, then could also be possible to do a sophisticated measurement of ingress and egress spectroscopy, where you see that the planet starts to cross the spectral disk, the stellar disk, and as it is in half, you only see one half of the atmosphere. As it leaves it, you see the other half. And by finding asymmetries in these kind of measurements, you could also potentially say something about that. But in general, yes, the core problem remains that you are working with a three-dimensional structure and you make everything flat, and then you get a number out of it. So trying to disentangle this probably will remain difficult, yes.
Okay, and then one last question, if I'm allowed. I continue on the question from colleague Jon Sundqvist. And also you started today that one of your aims is also trying to understand habitability and the origin of life. How do you define life?
Okay, there are a set of conditions that we usually think of when we think of life. For example, some parts of these are if it has a metabolism, if it can accept food or something that can count as food and excrete waste products and get energy out of that. So this can be a criterion. You can also have the criterion of reproduction. If something reproduces, it is life. Sometimes it's just by the fact that something has DNA. That could be a definition of life. I think taken together, that describes life on Earth quite well. But even on Earth, there are still some little viruses, for example, that are already on the edge of this kind of definition, because it's just as I understand it, is a cell containing DNA and made up of proteins. So this already is on the edge. I think it may not be such a big problem, because if we find one of them, it will already be a huge achievement. But
yeah, but here is it, eh? You started really excellently since you're describing to the public what are some of the emergent properties that we think is important in our definition of life. But actually what we are still doing as astrophysicists is we are looking to the very small building blocks that could, given some arrangements and then some transition phase that we do not understand yet, could give rise to life. So as an astrophysicist, we are still very much into this very little building blocks. And the question then, can we address life? Given the definitions that you just have given to the public, yeah, is still a big step.
Yes.
Which we won't be able, I think, to answer with James Webb, etc.
Yeah. I agree. And might not be totally clear if something like a detection of something special happens. Might not be totally clear that it is life, but that is okay, I think.
Okay, that's right. Chairman.
Thank you very much. I think Professor Nguyen is not connected, right?
No, indeed.
No. Okay. Now we'll ask a couple of questions myself. The first one is about the chemical composition that you showed at the very beginning of your presentation. You showed some usual molecules, let's say, and then titanium oxide, vanadium oxide. Do you know where those are coming from? Or they're a little bit unusual?
Yes, they are. Titanium and vanadium are quite rare with respect to all the other elements that I showed on that slide. The reason why it is included and counts as a detection in exoplanet atmospheres is because they have some properties that they are quite refractory, so they can easily form clusters. So this is why they are interesting. But they are also have a high opacity in the visible wavelength range. So their inference was first, they were inferred by the fact that you can have a temperature inversion in the atmosphere. You can see that if your water signal is in absorption or in emission, for example, and the fact that you have this temperature inversion makes it so that it's in emission, and you have to have some kind of opacity to create this temperature inversion. And it was thought quite early on that titanium oxide or vanadium oxide, which have this opacity, these optical absorbing properties, that they could cause this. I think this is also partly because it is used in the stellar community as well. I think you could be able to see it there via spectral lines in the atmospheres of cool stars, but I'm not totally sure about that. Then finally, with high resolution spectroscopy of exoplanet atmospheres, it was confirmed with a reasonable degree of certainty that it could be present in an exoplanet atmosphere.
Do you know where they're coming from? These molecules, this titanium, vanadium?
Where they come from?
Yeah. Are they created within the atmosphere, or are they there since the beginning of since the formation of the planet? Or?
I think they are just there since the formation of the planet, because we can already have some titanium and vanadium oxide in decent quantities by just assuming a solar elemental composition. And and just because these are so absorptive in the optical wavelength regime, they can already have an effect at relatively low concentrations.
Mm-hmm. And another question is that, it's related to what we will observe. So we don't know what we'll observe, of course, with the future telescopes. But in your opinion, what should we focus on if you had a choice? Is it better to observe a large number of exoplanets and do a low accuracy analysis, or to focus on specific ones and do a really high accuracy analysis, given the fact that we have a limited observation time, of course?
Yeah. Well, both would be the cheating answer, of course. I think maybe just one or well, maybe not one, but just a very limited amount of observations of these kind of benchmark planets, for example, as will happen for WASP-43b, would be very useful to constrain the physical processes on, let's hope that it is then a typical hot Jupiter. But then I think the many observations of a high or of a large amount of planets, of a big sample, would be very useful because, as we showed already, there can be quite some diversity, and I think it would be more dangerous to focus on one specific planet, thinking that we know everything about it, and then forget that it might not be so general at all. So I think then I would prefer to go for a large sample.
And a related question is that it's a little bit outside the scope, but you mentioned disks in your presentation, protoplanetary disks, that you can relate the composition of exoplanets to that of protoplanetary disks. Can you say a few words about that in general?
Yes. So as I already explained a little bit in Mila's question, then there is a chemical gradient in a protoplanetary disk, and depending on where the planet is formed, it will take up the gas of that specific chemical composition. So that seems to be like a direct link between the disk and between the chemical composition of the planet. However, that does not say anything about what happens afterwards. So if you have, for example, comets or asteroids, little planetesimals that are accreted by the planet during the dynamics afterwards, then that can still change the chemical composition. And what is also not totally clear yet is whether all these elements will end up like evenly distributed in the planet, so that the atmosphere will be representative for the composition of the whole planet, or maybe that it will form a core with all the heavy elements, and then the atmosphere will be depleted of heavy elements, for example. So this is also not totally clear.
Well, you anticipated my next question.
Okay.
Okay, thank you very much. I forgot to congratulate you on your very nice presentation and your manuscript. I now turn to the public. Are there any questions? Yes, there is a question on the chat about whether the name Hot Jupiters is unique, or if you, yeah, there we go. If there are also hot Neptunes, etc., etc.
All right, thank you for the question, Alex. The names are fairly colloquial, so we talk about the hot Jupiters because everyone calls it that. But there are some interesting names that have arisen before. So, for example, the hot Saturn has, I have read in papers about hot Saturns, just a smaller gas giant, but still quite hot. For example, you can also have super Earths or mini Neptunes. And they basically act as a large version of Earth or a small version of Neptune. And I've also heard the quite catchy name Neptini for a very small Neptune-like planet. So mostly the hot Jupiters, the super Earths, and the mini Neptunes are quite common, and some other creative alternatives may exist.
Okay, there is another question. Can spectroscopy be used to detect rings, if rings can even exist that close to a star?
So by this, I assume that it is meant rings around planets, for example, such as the case in Saturn. I think it might be difficult that close to the star, because at some point, at some temperature, the ring will sublimate if it gets too hot. However, we can actually try to use the transit detection method to find rings, and I think I've seen a paper about that once, where instead of, well, the ring also has some kind of area, and it also blocks some part of the light of the star, and it is, but it could be used to solve, for example, some problems where it seems that the planet is bigger than you would actually expect it to be, and then it might be that you are detecting a ring. But to my knowledge, such strong confirmed exo-ring detections are not yet have not yet happened.
Okay, and then apparently a very important question is, do binary planets exist?
Yes, in principle, yes. The problem is that then, in that case, we call the biggest one the planet and the smallest one the moon. But in principle, that is what a binary planet is. It's just a matter of semantics, because there is no real physical difference between a large moon and a small planet, for example. So there are some moons, for example, the largest moon of Saturn. It has an atmosphere. It is perfectly round in hydrostatic equilibrium. So it could actually be classified as a planet if it were on its own, but it's not. It's just around Saturn, so we call it a moon. But in principle, you can also call it a binary planet. And in that case, you can even call it a multiple system planet because there are many more moons around Saturn. So, no.
Thank you. And in the public, does anybody have a question?
I just may have missed it, but when you separated the hot Jupiter into night and day side, you used that the planet is locked, so it's like the orbital period is the same as the period around the star. Is it an assumption, or is it something that is often true, or why did you do that?
Okay. So it is in principle an assumption, but it's a well-informed assumption. So we have tidal effects between planet and a star. And if the planet is close to the star, the tidal effects get stronger. And basically, by tidal interaction and tidal dissipation, the planet will synchronize itself to the rotation period. The rotation period of the planet will synchronize itself to the orbital period. And that happens on a certain time scale. We can calculate that time scale with tidal interaction theory, and then see if this is a short time scale or not. For most hot Jupiters, the time scale is on the order of 1 or 10 millions of years, which is in astronomical timescales very short. So we can quite safely assume that they are tidally locked in a synchronous rotation. For the planets in my grid that were 400 Kelvin, for example, or some of them 600 Kelvin, the orbital distance is getting quite large, and there the assumption breaks down a little bit. But anything with a temperature above 600 Kelvin, it can quite safely be assumed that that will be tidally locked.
Thank you. Other questions? No? Nothing online either? Okay. And if there are no more questions, the jury will leave the room to deliberate.
Thank you.
Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for the doctoral degree in science, astronomy, and astrophysics. Mr. Robin Baeyens has presented to the faculty his PhD thesis on the topic of on the climate and chemistry of irradiated exoplanet atmospheres in partial fulfillment for the requirements for the PhD in science, astronomy, and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Robin Baeyens the degree of Doctor in Science, Astronomy, and Astrophysics. Congratulations. The session is now closed, and I will need your signature here. Immediately. Yet. Exactly. Now, yes, I will give the floor to the two supervisors who want to say a few words.
So, good evening, everybody. I'm Rosanna Caron, one of the co-supervisors, and actually I prepared a speech in Dutch. I will apologize if my Dutch is not completely correct, but I will do my very best. Zo, ik weet het nog heel goed toen Robin en Jels naar mij kwamen voor een stage en wetenschappelijk onderzoek. Mijn indruk was een heel enthousiaste, slimme en aangename student. En ik vond ook dat Robin heel bescheiden was. Misschien een beetje te bescheiden. Maar ik was heel blij toen hij dan koos voor een onderzoek voor de masterthesis met Leende Sien en mij. Robin weet wel dat het een heel moeilijk project was, maar hij lukte erin en haalde even verschillende prijzen. Helemaal terecht. Daarna koos hij opnieuw voor Leen en mij en voerde zijn onderzoek verder. Het was een reis van 4 jaar. We voerden sommige gevechten tegen zogenoemde referees, maar we overwonnen. Maar omdat wij ons exerceren, lukten wij ook de referees te overtuigen dat het onderzoek helemaal goed en juist was. En Robin kreeg ook meer vertrouwen in zijn vaardigheden. Dus vandaag ben ik heel gelukkig dat Robin zijn bestemming heeft bereikt. Een kritische, excellente, maar ook heel sociale wetenschapper te zijn. Ik ben helemaal zeker dat Robin in alles zal slagen dat hij zal voornemen. Dus van harte gefeliciteerd, Dr. Robin Baeyens.
Dank je wel.
Ludmila. Robin, samen. Ik vind het knap wat je hebt gedaan, Ludmila, om dat in het Nederlands te doen. Ongelooflijk veel bewondering. Ook voor jou, Robin, heel veel bewondering. Samen met jullie zal ik nu al een heel klein beetje de overstap maken naar wat er straks komt. En daarvoor heb ik een grote doos bij mij, Robin, en je zult me moeten helpen. Want ik kan mijn speech maar doen als jij die doos openmaakt. En die doos, die zie je daar staan.
Zal ik die... Tweede doos. Open. Welke had je graag gewild? Allemaal? Benieuwd waar dit heen gaat. Ja, ja. Alsjeblieft.
Robin, dit gaat over jouw oude jongensdroom. Na een van de pintjes begon Robin te vertellen, want Robin is geen grote verteller over wat hij vroeger zo graag deed. En samen met Marie heb ik dat heel goed onthouden. Want blijkbaar hield Robin ervan om poppenkast te spelen, maar hadden zijn poppen heel lange namen. Deze is Makikis Makikokis, volgens Marie. Dit wil zeggen, ik ben er ook en ik wil erbij. Want voor Robin was het best wel een uitdaging om zijn doctoraat bij mij te starten als eerste binnen het team, of binnen wat een team zou worden van exoplaneten. Hij zat zowat gedrongen tussen allemaal mensen die keken naar hoe sterren op het einde van hun leven doodgaan. En daartussen zat dan één knaak die erbij wou zijn. Die vanuit het eerst en heel lang alleen zijnde op dit onderzoek van exoplaneten telkens weer iedereen probeerde te overtuigen van hoe belangrijk het was. Wat je ermee kon doen, wat je ermee kunt bereiken. Maar alleen zijn in zo'n groep was niet altijd evident. Want we spraken soms een iets andere taal. Maar het is juist het leren verstaan van de taal van die andere mensen rondom jou, die jou heeft gemaakt tot wie je bent. Want als jij nu spreekt of het antwoord geeft aan professor Sundqvist over cloud formation, dan is het een antwoord gebaseerd op het onderzoek die we ook doen bij die oude sterren en hoe we denken daar te verstaan dat stofdeeltjes zich kunnen vormen. Onthouden?
Ja.
Makikis, makikokis. Deze is Willemijn van de Poelkapelle. Willemijn van de Poelkapelle geeft een mooie lange jurk aan. Nu, geen van jouw beide promotoren heeft zoiets. Maar wat die lange jurk van Willemijn van de Poelkapelle ons wel vertelt, is jouw lange manier van schrijven van papers. Weet je? Je moet het kunnen. 1 paper schrijven dat gepubliceerd is en daar zo'n impressionant boekje van maken. Je hebt een bijzonder elegante manier om schrijven, een heel consistente manier waarbij dat je telkens malen probeert om de klemtoon juist te krijgen. En natuurlijk, als je dan veel fysische processen combineert, dan kom je wel uit op 1 paper. En dat ene paper heeft heel lang op zich laten wachten. Dit is normaal. Als je start binnen een nieuw onderzoeksdomein en je start dan ook heel theoretisch, waarbij dat er niet onmiddellijk bijvoorbeeld waarnemingen klaar liggen voor jou, dan duurt het. Dit is de kracht van een onderzoeker. Dat hij of zij niet opgeeft. Na 1 jaar, na 2 jaar, maar na iets meer dan 3 jaar heel trots dit eerste zo belangrijke paper publiceert, die dan ook onmiddellijk wereldwijd heel veel aandacht heeft gekregen. Willemijn
Van de Koolkapelle. Dankjewel.
Midnight Stinger van, leg maar uit.
Dat is een cocktail.
Van Bourbon en
Ja.
Fernet Branca.
Fernet Branca, ja.
Midnight Stinger van Bourbon en Fernet Branca. Je mag Midnight Stinger zeggen.
Ja.
Onze Robin die drinkt wel eens graag dergelijke cocktails. En dit staat voor mij symbool aan het interdisciplinaire onderzoek waar we eigenlijk mee zijn gestart. Robin die keek niet alleen naar de fysica van die planeten, maar ook naar de chemie van de planeten. En dit is uitzonderlijk, want merendeel van de mensen doet het een of het ander. Robin heeft beide gecombineerd. En dit is ook waar onze toekomst naartoe gaat. Naar jonge mensen die durven een stap te maken verder dan 1 disciplinaire silo, maar die verschillende disciplines durven combineren. Het is niet gemakkelijk, omdat de referees daar ook vaak heel sceptisch over zijn, omdat je ook als persoon soms denkt, ben ik nu het ene of ben ik nu het andere? Ken ik voldoende van beide? Ja, het is altijd een zoeken, maar het is dat zoeken die zo verrijkend is. Als Midnight Stinger, Robin, heb je ons exoplanetenteam geleid. We zijn gestart met 1, je ziet hem staan, mijn eerste dokter in het veld. We zitten nu op onze 2-wekelijkse exoplaneet-meetings met een 10-tal, 12-tal mensen rond de tafel of rond de online meetings. We zijn niet alleen meer van de mensen hier van sterrenkunde, maar ook de mensen van biofysica, de mensen die bezig zijn met materiaalkunde, de collega's van chemie. Ja. Het is boeiend, het is uitdagend, ook om daar weer elkaars taal te verstaan. En het is ook omdat Robin dat kan, dat ik heb gevraagd dat Robin zou starten als postdoc onmiddellijk in deze groep. Omdat we nu in die heel belangrijke overgangsfase zitten van het verstaan van verschillende disciplines, de taal te leren verstaan, om nu samen wetenschap te kunnen bedrijven. De laatste. Genaamd Oude Jonkheid van HD209458P. Ja. Oude Jonkheid van 209458P. Ja. HD209458P is natuurlijk een van de meest gekende warme Jupiters waarover Robin onderzoek heeft gedaan. Nu, HD209458P is jong. Jong, ook al is hij miljoenen jaren oud, maar jong omdat zijn ster nog best heel lang kan leven. Maar hij zal oud worden. En dit is waar we nu ook met nieuwe PhD-studenten naartoe willen gaan. Als die moedersterren oud worden, en daar heeft Robin me de laatste maanden al heel hard mee geholpen, als Jupiter oud wordt, wat gebeurt er dan met Jupiter? Zal Jupiter veranderen in temperatuur en in chemie? Maar niet alleen met Jupiter. We willen de vraag beantwoorden over die oude jonkheden, wat ze doen. Wat zal de aarde doen eens onze eigen zon oud wordt? Ja. Dit is weer een grote stap in het onbekende en samen met Robin durf ik dit aan. durven trachten nieuwe onderzoeksdomeinen aan te snijden, om samen met dan een team van andere mensen daar op zoek naar te gaan. Natuurlijk kan ik dan niet afronden met hetgeen dat Robin nooit heeft gehad. Hij heeft me op die bewuste avond verteld dat hij nooit een echte poppenkast heeft gehad. Stel u voor. Dus Robin, in dat doosje, en dat kun je dan, daar, het staat daar, de poppenkast. Poppenkast en hoe je speelt, doet mij denken aan hoe Robin bijvoorbeeld vandaag zijn lezing gaf, hoe hij onderwijs heeft, hoe hij lezingen heeft. Altijd bijzonder didactisch, altijd goed verstaanbaar, ook als we gaan naar studenten, als we gaan naar leken, als we nu proberen de bruggen te maken naar andere disciplines. Dit is een ongelooflijke kracht van Robin. Hij kan, en dat is uitzonderlijk, op die leeftijd, jonge leeftijd, reeds te beseffen welk taalregister je moet gebruiken om je verstaanbaar te maken. Ik ken veel collega's die het gedurende hun hele carrière nooit kunnen, nooit weten hoe leg ik het uit op de manier dat jij het verstaat. Robin, dit kun jij. Ik vind het ongelooflijk knap. En dus samen met dit alles wil ik jou van harte dankjewel zeggen en ook van harte bedanken met wat je hebt bereikt.
Wow. Thank you very much for these beautiful words. I'm a little bit overwhelmed by all these nice things that you both have said about me. I'm also aware that I am the only thing that stands between you and the reception, so I will keep this final word quite short. And just say thank you to a number of people. Most importantly, to my supervisors, of course, for all these nice words and for all the beautiful advice that you have given me, scientific or otherwise, over the last few years. Ludmila, you said that you were happy that I chose you two as a PhD student to do my PhD with you two. But actually, I was happy that you chose me to have a PhD student as a PhD student. So I think, yeah, it's beautiful that it goes both ways. Of course, it means that it was a great collaboration, and hopefully not over yet. Of course. Yes, I also want to thank some other people. So all the members of the jury, of course, for having read my thesis, for having given very detailed feedback, all the questions, which were not only terrifying, but also very useful for me, because I can think about it and incorporate them in future research, of course. I would also like to thank all of the audience, my friends, family, who all came here to see me, which is somehow incredible to me that you would do that. Some even have taken off from work just to be able to be here. Thank you very much. It's amazing. I, of course, would like to thank also the people at home who are looking at me and listening to me. I don't know how many. Well, so 10. Okay, good. So you 10, thank you. And also Steve, of course, if you're watching. And I would also like to thank all the colleagues from IVS, all the friends that I've made here during my PhD. Luckily, I will stay for 1 more year, so we will still get to have fun times together. Thank you also to my parents. There they are, Peter and Inge. For just always supporting me in my choice of studies. This is astronomy. This is really what I wanted to do, and you always supported me in that. Thank you, Mama, for the beautiful thesis cover that you made. It's really amazing. It looks exactly like what I wanted, and it's also how I said it. I want this and this and this, and you just gave it to me as if it was nothing. So thank you very much. Am I forgetting someone? Of course, I would like to thank my girlfriend or fiance, actually, Lisanne, especially for the last few weeks or actually maybe months, which were probably not the most nice to live with me together in a closed space. But I mean, you supported me every time that I needed and helped me wherever you could, and yeah, it's amazing. So I think that was enough sentimentality. I think now it's time more for a party. So everyone at home, see you later. Thank you for watching. Everyone in the room, there is a reception, and you can go there by just following the corridor, and you will fall straight into the reception room. So have a drink, and yeah, thank you for joining. I'm super happy.